So in this video, we're going to talk about heat, and we'll start by discussing the differences between heat and temperature. So heat is actually a form of energy transfer, and of course the type of energy is thermal energy. And it occurs due to a temperature difference, and we measure the heat in the unit joules. Now in contrast, the temperature is not a form of energy transfer. It is instead a measure of the average kinetic energy of particles, and we measure the temperature in degrees. Most commonly, we use Celsius and Fahrenheit, but in many scientific contexts, we will instead choose to use Kelvin. Now, we can get a better idea of what's going on here through the image at the bottom right. Here in the left portion of the image, we see a container with atoms at normal temperature. So we can say room temperature, for example. Then, on the right, we have that same container with the same atoms, except now the atoms are excited after the container has been heated. So the average kinetic energy has increased, which is to say the temperature has increased. So we can see these particles have more energy, and therefore they're making more forceful collisions with the sides of the container. And you can see if you provide enough energy, the container will actually start to bulge because the force of those impacts is so large. Now, a very important thing to understand is that more heat energy does not always mean higher temperatures. So we can think of this through an example. If we compare a bathtub full of warm water versus a teacup full of boiling water, which would have more heat energy? Well, the teacup would certainly have higher temperatures if it's boiling and the bathtub is only filled with warm water, but it has a much smaller volume. So it's actually the bathtub with the greater volume but the lower temperature that's going to have more heat energy. Then another very important thing to understand is how heat transfers, because it transfers in a very particular way. It transfers from hotter to cooler objects, and it does so until thermal equilibrium is reached. Remember, the heat is a form of energy transfer, so it has to occur based on a temperature difference. And if there's no temperature difference, well then there's no heat transfer. So equilibrium is where there's no temperature difference, so no heat transfer occurs. Now the rate at which this occurs depends on many factors, with one example being the surface area, which is what we see in our example here below. In the left ice block, we can see a cube, and in this right ice block, we can see a rectangular prism. So it is B that has a greater surface area, and therefore thermal equilibrium will be achieved faster with B. It will melt more quickly, because the larger surface area means the heat can more effectively change this state. More energy is absorbed more efficiently. So we said that heat conducts from hotter objects to cooler objects, but let's talk more about some of the specific modes of heat transfer. So the first mode is conduction, and conduction is the diffusion of thermal energy either within one material or instead between materials that are in contact. So we can refer to our campfire example here down below to take a closer look at conduction. So we can see we have one person holding this metal rod, and we see one end of the rod is closer to the fire. So this is the end that will get very hot, and then heat can conduct through this metal rod to the cooler end, to the side where the person is holding it. Now, this covers conduction within a material, but what about between materials? Well, this is exactly why this person is wearing a glove, because as heat conducts and this cooler end becomes very hot, it could burn the person's hand. So to prevent conduction, they're wearing a glove, which is going to be made of an insulating material to prevent heat transfer from the rod to the person's hand. Now, I mentioned that the glove is made out of an insulating material, so let's talk a little bit more about that. Well, here on the left-hand side of this top right image, we have a piece of wood, and to the right of that, we have a metal rod. The wood is an insulating material. It's not going to conduct heat very efficiently because, unlike a metal, it does not have free electrons that can efficiently conduct heat. Instead, the metal rod is the conductor, and for this reason, metals are often used in electronics or many other different applications where heat conduction is a primary function. Now then, the second mode we should talk about is convection. And in convection, heat transfers in fluids, so we're talking about liquids and gases, and it occurs due to differences in density. So again, we can refer to our campfire example, and we can see that we have convection. We have these hot gases, which are expanding in volume and therefore decreasing in density, begin to rise because they are less dense. But as they rise, they will begin to cool and become more dense. And that's why this is a cyclical process. We have convection cycles or convection currents that essentially recirculate back from high to low as the gases change in temperature. Now, this is exactly what's happening in a hot air balloon. We have a heat source located at the base of the balloon, and this will increase the average kinetic energy, increase the temperature of the air within the balloon. This will increase the volume, and therefore it will decrease the density, and it will float. Then lastly, we have the final primary mode of heat transfer, which is radiation. So we're talking about heat transfer through electromagnetic waves, and specifically the infrared part of the spectrum, infrared radiation. Now remember, unlike mechanical waves, electromagnetic waves do not require a medium to travel. They can travel through a vacuum, for example. So again, returning to our campfire example, we can see the heat from radiation. And in fact, this is the primary reason why a campfire is hot and how we sit around it to get cozy or warm our gear or what have you. It is the infrared radiation coming off the fire that is providing this warmth. So now let's talk about thermal expansion. Materials expand when heated as particle motion increases, when the average kinetic energy increases. And oppositely, when cooled, instead of expanding, they contract, they shrink essentially. Now, between the three states of matter, solids, liquids, and gases, solids will expand the least, liquids the second least, and gases will expand the most. Now, why does this matter? Well, there are many practical examples of this. For example, we have expansion joints, which are used in bridges and essentially account for these size fluctuations that occur due to temperature changes, and this serves to prevent cracking. And then we also have the fitting of metal parts. For example, if you were to fit a metal part on a particularly cool or particularly hot day, this could definitely affect your ability to do so. And in the same way, heating and cooling can actually be used as a tool to fit metal parts. By manipulating that expansion and contraction, they can achieve a more reliable fit. Now, we talked about the difference between solid, liquid, and gas. Again, solids expanding the least, liquids expanding the second least, and then gases expanding the most. But what about when a material goes from one state to another? Well, for most substances, solids will have the smallest volume, liquids will have the second smallest volume, and then gases will have the most volume. So we're talking about one material in each of these three states. But there's one very important exception, and that's water. Because unlike most other substances, water actually expands when freezing. It expands when going from the liquid to a solid. So ice, frozen water, actually has more volume than liquid water. And again, this is essentially an exception. Most substances behave in the opposite manner. So let's take a look at our example here on the right. We have a container of liquid water. And if we were to ask ourselves which of the images, A, B, or C, reflects what this liquid water bottle would look like after being frozen, which would be our correct answer? Well, the answer is C. And we know this because, again, water is that exception. It expands when freezing. So the volume has increased, and therefore it must be C, reflecting the larger volume. So now let's summarize some of the key points from this lesson. First of all, we made the distinction between heat and temperature and said that heat is a form of energy transfer, and specifically thermal energy transfer, and it occurs due to temperature differences. The unit for heat, we said, was joules. Then we said temperature, instead of being a form of energy transfer, is a measure of the average kinetic energy of particles, which is typically measured in degrees, most commonly Celsius and Fahrenheit, and for scientific purposes, often Kelvin. Then we talked about the nature of heat transfer and some of the modes of heat transfer. And in general, we said that heat transfer occurs from hotter to cooler objects, and it does so until thermal equilibrium is achieved, until there's no longer a temperature difference. Now, there are several factors that will influence the rate that equilibrium is established, and the example we covered was surface area, where the larger the surface area, the more quickly the thermal equilibrium will be established. Then moving on to the modes, we talked about 3 key modes: conduction, convection, and radiation. For example, we said that conduction is the diffusion of thermal energy, either within one material or instead between materials that are in contact. After that, we went on to discuss expansion as a consequence of temperature change, and said that most substances have solid states with the smallest volume, liquid states with the second smallest volume, and then gases, which will have the greatest volume. Again, we're talking about the same material in each of these 3 states. And then we pointed out one very important exception, which is water, because water expands when freezing. So ice actually has more volume than liquid water. In most cases, going from liquid to solid, the volume would decrease. But again, water is an exception, and the volume will actually increase.